Welcome to this video. We're going to solve number 28 from your notes handout. This circuit has three resistors, X, Y, and Z. They all have the same resistance, 4 ohms. The cell or battery has an EMF of 18 volts. We're asked to find the current in each branch of the circuit. So we're going to start out by drawing how current flows through this circuit. That's a natural starting point to find the current. The battery has a positive terminal where charges have high potential energy, or lots of it. Because it's big potential energy, we draw that as a bigger line. And the battery has a negative terminal, which is where charges have no energy. The positive charges flow out of the battery, the positive terminal, and they all flow through X. So the current through X is I sub X. After the charges flow through X, they proceed toward this junction. And at that junction, they split off. Some current goes through Z, and some current goes through Y. So here, this arrow is the current through Z, and the other charges go down, and the current through Y is I sub Y. After the charges pass through Z, they continue toward this junction along this path. And after the other charges go through Y, they continue toward the same junction. At that junction, the charges meet back up, and they recombine to form the full amount, Ix. Remember, Ix is a total amount. That's how much you had before you branched off. So when you come back together, it has to be the same amount, Ix. Charges can't disappear into thin air. They can't appear out of nowhere. Charge is conserved, and so these two values are the same. The first thing we're going to do is find the total resistance of this circuit. The total resistance is a little tricky here because we have two things going on. Z and Y are in parallel with each other, but their parallel circuit is in series with resistor X. That's kind of hard to see, so let me draw it like this. Here's our battery. Here's resistor X. After charges go through X, they go through this parallel circuit, which I've left blank. There's a branch through Z and a branch through Y. But instead of drawing the two branches, I'm just going to draw a single resistor that I'll call YZ. And so now we can see that this parallel circuit is in series with X. That means the total resistance is equal to the resistance of Y in parallel with the resistance of Z plus the resistance of X. This notation stands for the total resistance of Y and Z together in parallel. We add that total resistance to X. Y and Z both have a resistance of 4 ohms. Whenever the two branches of a parallel circuit have the same resistance, their total is half. So 4 ohms, the resistance in any one branch, over 2. That's the total resistance. The resistance of X is 4. And together, adding this all up, we get 6 ohms. So there's our total resistance. Now that I know the total resistance, I can find the total current, which is really no different from Ix. The total potential difference dissipated by the circuit is equal to the total current times the total resistance. The total potential difference is equal to the total EMF. If you supply 18 volts to the circuit, then the circuit will dissipate all 18 volts. So this value here is 18. I total is no different from the current through X. All of the current in the circuit goes through X before branching off, and then it joins back up and it all goes through X again. The total resistance we just found, that's 6 ohms. Dividing both sides, Ix is 3 amps. Now we just have to find the resistance through the current through Y and the current through Z. We know that the potential difference across Z and the potential difference across Y are equal because they are in parallel. Whenever you have two parallel resistors, their potential difference is equal. But on the left side, we could replace V with I times R, because V equals IR. And on the right side, we could replace V with I times R, because V equals IR in general. Let me try my R again. And we know that the resistance of Z and the resistance of Y are equal, so those cancel out. And look at what we have. The amount of current through Z equals the amount of current through Y. So if you have 3 amps heading toward the junction, exactly half goes through Z, and exactly the other half goes through Y. I already know then that the current through Y is 1.5, and the current through Z is an equal amount, 1.5. But let me go ahead and just use some math to prove that. We say that Ix is what enters this junction, and the amount of current entering the junction equals the amount of current exiting the junction. So Ix equals Iy plus Iz. Iy plus Iz. But Iz is equal to Iy. So the right side is really Iy plus Iy, or 2Iy. And if Ix is 3 amps, we can easily solve for Iy. Iy, you divide both sides by 2, you get 1.5 amps. And then, based on this, Iz equals Iy, which is also 1.5 amps. So that's how you solve this problem.